I don't know. No,
I mean,
I believe you.
I was buying something from Micro and he mentioned that he would kill for one of those in Slash or whatever. I owed him money away.
So who did you ask him to kill?
My server now. We're working on it.
Oh, I did that already.
How many times?
Only once. It was live.
Yeah. When you put all the challenges at the same time and
Yes.
it decided to kill itself. But
Oh.
it came back.
I decided to procrastinate on doing all the health checks and stuff, and
We'll do it later.
no, I made it look pretty. Like relatively.
I don't know when to send the message. Should I send it today? No, it doesn't make
Do you
sense.
found challenges for the? Do you want me to help you?
I'm going to use part of the ones we already found and then
Right. Okay.
and take others.
Okay. So, quick reminder. First of all, we've learned a question that will be on the test. And you should click on the following link and solve questions number 5. And they are all about this theorem, which says that given a monotonic sequence, i.e. only rising or only decreasing, it's either bounded and converges to a finite limit, or it's unbounded and tends to either infinity or minus infinity, whether it's increasing or decreasing. And I showed you how do we use this theorem in the last example to prove that a sequence must tend to infinity without actually proving that the sequence is large, but we only say it's increasing and it couldn't possibly have a finite limit because no finite limit will uphold this equation. So this was the theorem that we've shown and proven. It's very important by itself. It will lie in the base of a few proofs in the future. But for now, I'm getting back to the number E, the Euler constant, and I wish to prove that the series of the number E is increasing and bounded and therefore has a finite limit. So back
Does E stand for Euler or does it stand for exponential?
we talked about it.
No, as in like what it literally stands for.
I'm not sure. It's I think Euler used it as E. I'm not sure.
But he called
before
it E
it-
after himself.
I'm not sure. Before him, it wasn't called E. That's what I know, but I don't know more than that. I didn't read a lot about Euler, sadly. So it's the Greek letter, and the Greeks invented all of the mathematics. No,
Because they decided to call it pi, bro. It's a letter. I don't know.
I don't know. I like that you asked me as a lecturer and things I know nothing about. I could invent something and you would believe me.
So yeah, so why is the letter?
It's when Archimedes came to Germany and he saw a pie. It was so delicious. Yes.
I might have complained if it
Yeah.
wasn't correct.
Yes. Back to Euler constant. So for now, we fix an to be, and for some time, an should be 1 plus 1 to the n over in the power of n. And we wish to prove it is increasing and bounded. So how will we do that? We will use the means in inequality. We saw in Wikipedia last time it was GM, AM, geometric, arithmetic, and harmonic, AGEM inequality. which says, I won't prove it, I've shown you where you can find a proof if you like.
Billion?
Theorem, no, probably also about a math one. That's a proof I wrote. Wikipedia have more and more proof. When I started MathWiki, a lot of time it didn't have proof, just theorem now, but sometimes mine are more attuned with students because sometimes they prove things using like this very high mathematics way, but any case, theorem. For any um, sequence of n positive numbers, I would lose the word sequence on it. For any n positive numbers, x1 to xn all larger than 0, it is true that n over 1 over x1 plus 1 over xn is smaller or equal to this n root of x1 times xn, which are smaller or equal to x1 plus xn over n. The one you are supposed to be most familiar with, the expression you are supposed to be most familiar with is the right-hand one. That's the algebraic mean. That's when people usually say average, they mean this formula. Sum up all the values and divide by how many values you have. But there is also the geometric mean. When you multiply all the numbers and take the roots, and root, and the harmonic mean, which is the less known one, but it's needed for this proof, is something weird. You're taking the inverse of the numbers. You take a regular average, an algebraic average, and then you inverse it again. So it makes some sense, right? In order to take the average between 8 and 7, I will do the average between 8 and 7th, and then I will inverse it back. So it makes some sense. In any case, the harmonic one is always smaller than the geometric one, which is always smaller than the algebraic one. And equality occurs.
Occurs. No, without.
Oh, occurs, right, you're right, occurs. If and only if all the numbers are the same number. Right? If I do the average, if I got 60 on linear algebra and 60 on calculus, my average is obviously 60, right? And it doesn't matter, sorry, by what average I'm going. Okay, but if at least one of the numbers is different, like if I got 60 on that and 60 on that and 59 on computer science, then then there won't be any equality here. That will be strictly lesser than this, that will be strictly lesser than this. Okay. So I'm not proving that for all prove other interesting things. Go here, and I'll give you the link. He should be on the same. So Wikipedia is first, but I'm in the first pseudonym, and MathWiki is second, so it's fine. Yeah.
One after the position. I'm one and the SEO on the side. Not reason.
Okay. I shouldn't mark the things. So just to go here, just to here. Here. Fine. I'm sure it will be clicked on many times. In any case, now look at the following. Marvel on. How do I write Marvel?
Yeah, it's like that. Like that.
Oh, it doesn't include the M for some reason.
Maybe because it was written in the Hebrew. Yeah. Sometimes.
Yeah, I don't know. Marvel at the following trick. And I would like to show you in the wiki, I took a quote of late mathematician, Israeli mathematician, it says, נהוג לומר כי אם פותרים בעיה מסוימת אחת באופן מסוים אז זה תחכום, ואם פותרים שתיים בעזרת אותו רעיון זו כבר שיטה. It's common to say that if you solve one problem in a certain way, then it's a trick. But if you solve two problems in that way, then it's a method. So I really like this idea, and it's really relevant to the mean average, the GMA inequality, because it's actually used for a lot of different things. You can read about it here. Quite interesting. Like if I have a triangle and a rectangle with the same edge, who will be bigger or larger and stuff like that if they have the same area, sorry, then the circumference of the triangle will be bigger than the circumference of the square. I wonder why. I wrote it myself long ago, but I said square, but this is a rectangle. Wonder why. Whatever. Yes. So what I'm preparing you mentally for that. What we're going to do will seem like a trick, but you won't have to be able to think of tricks like that yourself, unless you're going to invent another constant like Euler. It's super specific to the Euler constant theory. I don't know anywhere else within this course it will happen. We will calculate the means and geometric mean and algebraic mean of the following n plus 1 positive numbers. X1 would be 1 plus 1 over n. X2 would be 1 over 1 plus 1 over n. Xn would be 1 plus 1 over n, original, right? But so if I'll calculate the mean only of these numbers, it will obviously be 1 plus 1 over n, like I said, right? But the last number is different. It's 1. Okay? So I'm calculating the average of these numbers. One might ask himself, even one of you guys here, why? Why the hell should I calculate the means of these numbers? But that's the trick. I'm allowed, do you agree that I'm allowed to calculate the means of these numbers? Someone said, and they like look at it, no. Who allowed you to calculate? Yes. No, n is not an infinite. As n is a number.
Wouldn't it be nice?
Yes, no, it wouldn't be nice. Given some, given some natural number n, so it's a fixed number, and calculate the means of the given. I wrote it in a bad place. Sorry. And we'll given, it should be at the start. Given some natural number n, we will and calculate the means. Okay, so it's not infinity, it's some number. Okay, so n doesn't move. So I calculate the means, and after I will calculate the means, since these are not the same number, there will actually be a strict inequality here. The geometric average will be strictly smaller than the algebraic average. That will be a fact. So why do I care about it? Because this fact will prove that the Euler constant sequence is increasing. Surprising, but you will see it happens in a few seconds. Yes. So first of all, the geometric average. What do I do in order to calculate the geometric average? It's not square root.
N plus one.
It's the n plus 1 root of the products of all the numbers, right? That's the geometrical mean, which is the n plus 1 root of 1 plus 1 over n times 1 plus 1 over n times 1. You can see now, by the way, why did they choose the last one to be a 1? Because here you get 1 plus 1 over n to the power of n. And when the last number is 1, it remains unchanged. That's the trick, which is a method, because we'll do it again in a few seconds afterward. And so that's the geometrical average. And the algebraic average, or mean, is the sum of the numbers over the amount of the numbers. And in here, it's 1 plus 1 over n time plus 1 plus 1 over n plus 1 over n plus 1. Agreed? And I will simplify it a bit. And just remember that the geometrical mean is strictly smaller than the algebraic mean. So I will simplify both of these expressions. Here it's pretty simplified. I will just write 1 plus 1 over n to the power of n. I will simplify this, and I will say that the geometric mean is smaller than the algebraic mean, and I will obtain exactly what I wish. You will see. So, and that equals, I'll start with simplifying the right-hand side, the algebraic mean. So I have n times 1 plus 1 over n plus 1 over n plus 1. Do you agree about this simplification? And distribution law, n plus 1 over n plus 1. I might be tempted to say that n plus 1 is n plus 2, but that's not the way to go. I'm saying 1 plus 1 over n plus 1. Agreed? So since GM is smaller than AM, we get that the n plus 1 root of 1 plus 1 over n to the power of n is smaller 1 plus 1 over n plus 1, and take the power of n plus 1 on both sides, and we get that 1 plus 1 over n, or then, sorry, is smaller, right? 1 plus 1 over n plus 1 in the power of n plus 1.
That's crazy.
Okay. And just what? Here?
Yeah.
Why can't we just say it's 1 plus 1? We just like subtract 1 on the bottom and just
Well, you separate it into two fractions. N plus 1 over n plus 1 plus 1 over n plus
okay.
1. If it was n plus 2, I would tell you, wouldn't it be nice? And I will change to n plus 1 plus 1. It's a common trick, but here we got it, so we just need not to destroy it. Nice avocado.
Thank you.
Okay.
I'll eat it
it's a
later.
free shop. Okay, good.
You can eat it, I don't mind.
It just feels wrong, you know.
It's a huge avocado.
I like to buy them big.
Yes.
Jesus Christ.
This is- The problem with such comments is that in the video, just my voice is recorded, not the students. Sometimes they say something horrible and then whatever. Okay. So look, that means basically that means that an is smaller than n plus 1. That's what we have here, right? It's the next element of the same sequence. So the sequence is indeed increasing.
But like it's oddly fitting.
Yeah, not that's the thing. The mean value, not the mean value. Now I get what I'm confused. Mean value theorem is another theorem. The average theorem, the inequality, is known very important for a lot of things, and I guess someone thought of putting it here, the value of the sequence. There is another proof using Bernoulli's inequation, but a lot of people, that's what they did. They lived. Nowadays, everyone wants to go to high tech and make a lot of money. But for a lot of time, people study math for math. It was interesting. Euler and Fermat, they wanted to know how numbers work. What happened when you take a prime number to the power of something? And you know, RSA encryption works on these results. But yeah, there were people just solving problems for the sake of problems. Okay. So probably they. That's the person who thought about it. Okay. So we have that. We need to prove that it's bounded. That will also use a trick, an even more horrible trick, I think, but nice. Now let us look at the sequence, which I will call Bn. It will be 1 plus 1 over n to the power of n plus 1. Not that different than an. Do you agree? Actually, it's 1 plus 1 over n times 1 plus 1 over n to the power of n, which is 1, and therefore Bn equals 1 plus 1 over n times an. That's the connection between the two sequences. We proved that an is increasing. What do you think about Bn, which is rather similar, right? What do you think about the sequence Bn?
It's also increasing as well.
Yeah, so it's decreasing, right? That's surprising by itself. And to give you a quick circumstantial evidence for it, if you substitute n equals 1 into an, you get 1 plus 1 to the power of 1, that's 2. That's smaller than e. It makes sense that it's increasing to e. If you substitute 1 into n here, you get 1 plus 1 to the power of 2, which is 4, which is larger than e. Then Bn actually decreases to the number e. And how do I know they will have the same limit? Because this tends to 1. So if an tends to e, then Bn must also tends to e. So that's circumstantial evidence. It's obviously not proof.
So wait,
But we will prove that Bn is decreasing, and you will see why is that helpful.
so okay, so Bn is decreasing but goes also to E.
Yes. Yeah, so it's an goes here, Bn goes here, and I'm e. Okay, then it goes from the same side for the two sides, from different sides to e. One goes from above, one goes from below. That's what actually is happening. Yes.
The proof that they goes to E.
No, no.
Oh, it is.
But it's a bad question. We don't need to prove that AN goes
Okay,
to E,
okay.
right? We just need to prove that AN has some limit, and the limit would be E. But we didn't even prove that it has some limit. We just proved that it's increasing. It could possibly, for now, increase to infinity.
Yeah.
But in a few seconds, you'll see it is bounded, and therefore it has a limit, and the limit will be defined to be yes.
We'll know.
E will be defined to be the limit. Yes.
Do we know that it's bounded because of the fact that AN is increasing and BN is decreasing, but
Yes.
they never actually overlap?
And more than that, yes, and more than that, therefore, Bn is always larger than An. Agreed? Because Bn is taking An and multiplying by a number bigger than 1. So in fact, what will happen is that An is bounded by the elements of Bn themselves. Specifically by 4, which is the first element. What? Yeah, for Bn.
Yeah. It's
Yeah,
two
all of
times,
Bn will be smaller than the first element of Bn. That's why it's bounded, and that will be the end of the bounded proof. Okay, so how will we prove that Bn is decreasing? Let's calculate the harmonic mean and geometric mean of the following n+2 numbers. x1 equals to xn+1, and they are all equal n+1 plus 1 over n. And xn+2, what would the last number be? 1. Okay. So let's start with the geometrical mean. That's the easier one. It's the n+2 root of the multiplication of it all. 1 plus 1 over n to the power of n+1, i.e. Bn, times 1. And you see, it's kind of like the same method now, like Ben Albel said, right? It was a trick before, now it's a method because we used it twice. But in this course, it's not actually a method because we will use it only twice. And now, and that's it. Okay. Yes. Harmonic mean, the harmonic mean. By the way, these are the kind of things they do at the Math Olympics. Like a lot of people say that being good at the Math Olympics is knowing a lot of these tricks that are not well known in mathematics, but they are well known for whoever study for the Olympics. And then they use different tricks until they found the one that works. And I'm not saying it derogatorily, but yeah, it's from this kind of book that I took it. It was the dissertation of the PhD of Ben Albel, and he took many mathematical problems or riddles or Olympiad problems and show how to solve them and how you use the same method a few times. And the proof about E itself, the series what I'm showing you is from this book. I don't know if he thought about it himself or took it from somewhere, but I took it from that. So the harmonic mean would be n+2 over the sum of the inverses, meaning 1 over 1 plus 1 over n plus 1 over 1 plus 1 over n plus 1 over 1. Okay, I will show you if you don't remember from where I got it. The harmonic average, I'm taking the inverses of all the numbers, summing them up, and I divide the amount by the sum. Okay. It's a good question. I usually put it in the class, but because we're a bit behind, I didn't. but I will, if you wish, I'll show you after class more, but I will tell you in 2 seconds. Say my way to work, I drove at an average speed of 30 due to traffic. And on the way back, I drove at an average speed, a fixed speed of 30. And on the way back, I drove on a fixed speed of 80. What would you say my average speed that day was?
If your time of traveling is equal to.
There is no if because you can calculate yourself. Because you know that the distance from my house to work is fixed.
Okay,
So you can actually
Yeah.
calculate it, and it appears to be the harmonic mean. You can calculate it and see it. It's nice. If you do it correctly. If you take the time you drove and divide it by the distance, then time by distance, distance by time, you will get the harmonic mean of 80 and 30. So that's where you use it. In any case, and now let's simplify this. How many elements do we have here? N plus 1, exactly. So this is n plus 2 over n plus 1 times over and 1 plus 1 over n plus 1. Little algebra. And so the numerator is still n plus 2. The denominator I can multiply by n. So I'll get n squared plus n. And here n plus 1, which is n plus 2 over n squared plus n plus n plus 1 over n plus 1, which is n plus 2 times n plus 1 over n plus 1 squared, which is n plus 2 over n plus 1. Wouldn't it be nice? N plus 1 over n plus 1. Okay, definitely did a mistake somewhere there. No, maybe not. I'm not sure, to be honest. N plus 1. Could be that it's true. I remember that I'm arriving at something different here. No, it's fine. It's fine. That's what I should get.
I don't understand why we're doing n plus 2 because B is n plus 2 elements.
Ah, yeah. Following n plus 2 elements. Yeah. Yes, okay. See, here and here, and this is n plus 1. So altogether, since the harmonic mean is smaller than the geometric mean, and this is the harmonic mean, we know that this expression is smaller, strictly smaller than this expression. And therefore, by rising it to the power of n plus 2, 1 plus 1 over n plus 1 to the power of n plus 2 is smaller than 1 plus 1 over n to the power of n plus 1, which basically says b n plus 1 is smaller than b for every. Agreed? Thus, together, for every n, it is true that A1 is smaller or equal to AN. Why is that true? What do we know about the sequence AN? It's increasing, so it'd be larger than its first element. But AN is always smaller than BN, because BN, which is smaller than the first element, B1 is 4, A1 is 2, therefore,
They're bounded.
therefore, an, sorry, an is bounded and increasing, and therefore have a finite limit. It's a supremum. And why do I have a supremum? That's thanks to the real numbers. If I take the elements of the sequence, the rational elements of the sequence, and only in the rational numbers, it would not have a closest rational number. It will not have a supremum. But in the real numbers, it does have a supremum. Stop touching each other.
What?
That's gonna be on the report.
Yeah.
Yes. Yes.
Ah, yes, that's from you on the first year.
Oh, sorry, you are allowed to continue touch each other.
In the
That could be even
in the
worse.
university allowed the place. Thank you
Yes,
very much.
yes. Okay. So I won't be anti-LGBTQ. So therefore n is bounded and increasing and therefore have a finite limit. We define the constant E to be that limit, i.e., so for the fun, E equals the limit 1 plus 1 over n to the power of n, since dn equals to 1 plus 1 over n times an. By arithmetics of limits, it tends to 1 times e, which is also e. So an tends to e from below, en tends to e from above. Since the limit of a monotonic sequence is its boundary, and then boundary, I don't know. Then for every n, it is true that an is smaller than e, which is smaller than bn. And why is this mention important? Substitute n equals, I don't know, 10,000. And we get that a 10,000 is smaller than e, which is smaller than b 10,000, i.e. 1 plus 1 over 10,000 to the power of 10,000 is smaller than a, which is smaller than 1 plus 1 over 10,000 to the power of 10,001. Okay, and that I can plug into a calculator, because that we know how to do, and but we rather the computer would do it. And we get 127,181.
It's funny, this definition is actually really good for approximating E.
Yes, it's not
That's why it's the
yes.
No, it's not like.
The definition of E is very good to calculate the value of E. Who would have thought? Yes.
Don't quote me on that.
I will most definitely copy on that.
One. Because it's even more ironic because it's actually the least best way to calculate it. There will be better ones, but it's the first because that's the definition. And it's 4. Okay. So now we've proven without a shadow of a doubt that the limit of this sequence, which we call the number e, is between these two numbers, meaning that the first 3 digits after the 2 is 718. So that's the first proof. I promised you that the number E that you knew from high school is the very number I'm talking about. But I think the more important one is not the digits, because we learn in calculus too how to find the digits of any number. The interesting thing to prove is why the derivative of e to the x is e to the x. But that will take us some time because we need to learn about derivatives beforehand. A theorem without proof. For any sequence an which is not 0 but tends to 0, it is true that 1 plus an to the power of 1 over an tends to e. And I think that is less surprising because an is smaller, it's small, it's close to 0. So think about it like being around 1 over n. So this will be about n. So it falls quite easily from this. It does. I do have to, with a full proof, I also have to deal with the negative numbers close to 0. But it always works. I don't have enough time to talk more about that because we need to continue. And that's that. And whoever wants to learn more, the full page in the Math Wiki in Hebrew, but the short videos show the full proof of this thing. Any questions so far up until now? I was confused within myself for a second, but luckily I remembered the time before I started the next subject, but I will tell you anyway. In the last year, I don't usually teach the calculus for math. I usually teach the calculus for engineering. So up until now, it's pretty much the exact same course. Now there is a difference. And so here, the next subject we will cover, but I'll do it rather quickly because there are more important things that I fear I will miss. But just in general, we will now learn about subsequences and sublimits. I will partial sequences. I will make sure the correct English term for that. And afterward, the next subject would be, so we won't do everything that is written here, but the next subject would be series, okay? And I'm telling you that for whoever wish to be prepared for the subject, so the next chapter will be series. Basically, this course is 3 chapters long. Well, it's 4, but the first one is negligible. And the first one is numbers and boundaries. The second one is sequences and limits. That's the one we're almost finished, but I will do the tatzdaot part. And the next one is series. That's sum of sequences, infinite sums. And then we will finally, by the 3rd trimester of the course, we will do functions and continuity and derivatives, which in a lot of sense is the main part of calculus. But like I said early on in the course, we are spending a lot of time refining the language, and then afterwards doing limits of sequences and limit of functions and continuity and derivatives will be quite easy because we'll be very much familiar with the idea of sequence. Okay, so that's that. Now just make sure how do you say תת סדרות and גבולות חלקיים in English. And תת סדרה, yes? Madeleine. And when they ask me this in Hebrew, I always correct them and say it's a turtle, but it's a bat. It's a female turtle. So if you assumed its gender, it's a female turtle named Madeleine. So that's the one in English. Subsequence. Oh, I was right. So what would be גבולות חלקיים? Oh no. That's DNA. That's not. What? That's
Maybe it's just using it as just Hebrew that we can.
that's a problem at Wikipedia.
Wait,
Oh,
go
Wikipedia
to
is
the top,
always
go to the top, go to
I
the top.
never no, but I never seen like
There's a
when you
problem.
switch a language, you get to a different
page.
term. No, because there here it's mathematical tatzidra, and here it's sequences of DNA.
It's applicational subsequent.
That's an application. Oh, well, this article has multiple issues. I agree with that. Okay.
We can agree on.
Wow, I wonder. So now I'm not sure if it's the correct term. Let's go to the highest totem of our times.
OpenAI.
Yeah, ChatGPT. Log in so we won't think that I'm. You won't lie to me. Okay. מה המינוח המקצועי באנגלית לנושא של
What do you think? What language do you think ChatGPT understands the most?
English.
It depends on how many resources there are like for that language, and most of the internet is in English.
subsequences, limit points or subsequence limits. Doesn't have a term. Like I wondered. I'm surprised. Okay, fine. It was just the name. The subject I know. And theorem. Oh. So next, we will talk for a while, not a long while, about subsequences. I think it's fine. Subsequences and partial limits. I did not use what ChatGPT said because I didn't like calling partial limit subsequence limit. It is their definition, to be honest, but it's a bad name. So partial limits. Yeah, I think it's and so that's what we're going to do. And like always, an introduction. The sequence an which equals 1/n tends to 0, meaning its limit is 0. Okay, the sequence I shouldn't break the line. Sorry, just a second. Tends to 0, its limit is 0. And the sequence an equal n tends to infinity, and its limit is infinity. What can we say about the sequence an equals -1 to the power of n? So it diverges, first of all, but it doesn't tend to infinity. So the limits formulation gives us nothing. we can just say it has no limit. It has no limit. But we could say more about this sequence, right? Because it's always -1 and 1. We wish to say it has two partial limits plus -1. Okay, so that's the very idea behind the partial limits. That's why in engineering we skip it because it's not so groundbreaking, right? But in mathematics and computer science, learn the exact same course of mathematics. It's important because we sometimes need it in the theory to talk about partial sum, partial limit, sorry. Where in engineering, I usually mention it when I need it without explaining too much. So with you guys, I will do something in between. I will teach you most of the important terms, but I won't prove most of them. Because there are more important things in my opinion. Okay. So first of all, we need to define a subsequence. Why isn't it clear? Say AN is the sequence N. Would 2, 1, 4, 3, 6, 5, etc. be a subsequence? I'll write it differently. Would this be a subsequence of 1, 2, 3, 4, 5, 6? What will you say? Will you say that this is a subsequence of this? No, it does contain the same numbers, but in a different order. And a sequence in a sequence, the order is very important. In Hebrew, I was a kid and say that's why it's called sidra, from the word seder, order. But in English, it doesn't translate. But the order is important. Okay. So the answer is no. The order of the elements in the sequence is crucial. That's one. Now, would 1, 1, 2, 2, 3, 3, 4, 4, etc. would be considered a subsequence of 1, 2, 3, 4, 5. What would you say about that? So now the order is the same, but every now and again I multiply an element. Again, no. Okay, subsequence is actually subsequence. I will give you the formal definition in a bit, but that's the idea behind it. And I will tell you how do we write it. Question? Okay. Lastly, would 1, 1, 1, 1 be a subsequent, not be, is a subsequence of -1, 1, -1, 1, -1, 1. Here, yes, because I take the numbers in the even places, then I get 1, 1, 1 as a subsequence. So how do I define it? I need to choose the indices, the places which I take the subsequence from, and the indices should be natural numbers because the place in sequence is always natural numbers, and it should be strictly increasing. I should take the next element of the subsequence further within the sequence. Okay, so now I can do a definition. Given a sequence AN and a sequence and a strictly increasing, strictly that it's never equal, it's always really increasing, much bigger, and a strictly increasing sequence of natural numbers Kn, we define a subsequence of the subsequence. I'm sorry, I'm rephrasing. We call A, K, N subsequence of AN. Okay, look at what I did here. I'm taking the sequence of places and putting it in. It's actually a composition. It's kind of a composition, and it's only allowed when the inner sequence is entirely made from integer numbers, because it must be a place. It can only be 1, 2. It couldn't be half, right? And it needs to be increasing in order to be considered actually a subsequence. For example, the subsequence of AN that contains the elements in even places is A of 2n, right? Here Kn is 2n, that's the way I go through the indices. Okay, only on the even places. Agreed? Any questions so far? Yes.
So Kn is a sequence of natural numbers.
Yeah, it's the indexes, it's the indices, it's
Yeah.
the places you take the elements from.
So do they have to be increasing? Okay.
Yes, these are all the questions I asked you before, right?
Yeah.
If it wasn't increasing, then this was able. This was a possibility, sorry, because you can take a number from the second place and then a number from the first place. No, you must continue within the sequence. Okay? And another example. Silly, but n plus 1. No, that's not silly. That's important. When I said silly, I thought about another example. An plus 1. Why is that a subsequence? Is the subsequence of an with that does not include the first element, first member of the sequence, because when you plug in n equals 1, you start with A2. Okay, it's also a subsequence. And last example, AN itself is a subsequence of itself. I never said you must delete an elements. You can take the entire sequence. It's also considered a subsequence. Agreed?
Like set.
Yeah. Okay. So now definition.
Wait, in the second example, do you mean doesn't?
That does not. Yes. does nothing. Okay. Definition L is called a partial limit of sequence AN if it is a limit of some subsequence of AN. Make sense? It's a partial limit if some of the elements tends to it. An infinite number, right? But a subsequence, by the way, it's always infinite. It follows from what I said, because sequence is always infinite because the n is a natural number. And here I told you that the Kn is the sequence of the places, it must be infinite. In any case, we know that subsequences are always infinite. In calculus, we don't deal with finite sequences, just in, I don't know, discrete mathematics and computer science and whatnot. Okay, so L is called a partial limit if it's a limit of any sequence AN, or subsequence of N, sorry. So for example, 1 and -1 are subsequences of -1 AN equals -1 to the N. Why? Because since A to N, which is a subsequence, is equal to -1 to the power of 2n, which equals 1, and A at places, even at odd, places, which is -1 to the power of 2n plus 1, -1. Okay, and just a second, and my follow-up question would be, okay, and the follow-up question would be, could there be any other partial limits in this case? And I won't answer it immediately, but that's a question to try. I proved to you that 1 is a partial limit. Partial limits. That's what you wanted to say, Simon? I wrote subsequences by mistake, but I meant partial limits.
No, I want to go.
Okay. So I've shown you a subsequence that tends to 1, and I've shown you a subsequence that tends to -1. Therefore, by definition, 1 and -1 are partial limits of this sequence. But could there be any other partial limit to this sequence? And we'll speak about it later. The answer is no. Yeah, there couldn't be, but why? We'll answer that. Yes, sir.
So with cyclic functions like sine or cos, do they have infinite limits?
So you look at wait for the next thing I'm about to show you and ask you. Could no, we will see why later. Okay. I'm taking a Sami question almost as is. Could there be a sequence with an infinite amount of partial limits? Sami suggested sine and cosine, but it's so complicated because sine is if you use radians. If you use degrees, then after 360 you get back to square one and you get 360 different limits and no more. Maybe even less, to be honest. But definitely less. But if you use radians, then you don't get back to the same place you were exactly, and there could be there are infinite limits, but it's quite hard to prove. Could you think of an easy example where a sequence would have infinite number of partial limits? So I'll take that as a no, and I will write it myself.
Didn't give us much time to think.
Yeah, I agree. I'm not judging. So the first element of the sequence would be 1.
Yes.
We got that.
No, I thought your catchphrase. That's what I meant to say. Okay. And the next element is also 1 and then half. And then 1, half, third. 1, half, third, quarter, and so forth. The partial limits of this sequence are 1, obviously, do you agree? Then half, because there are infinite number of halves. You can just take all the halves and you have the constant sequence half that tends to half. And similarly for every fraction, right? Are these all of the partial limits of this sequence? What else?
When you say all these, I mean just those 3 numbers.
Yes. No. 3 dots and so on. Obviously, including quarter and 1/5 and so forth. Are these all the partial limits? 0, nice. And I will tell you now, I'm not sure if I will prove it or not, but I will definitely say it. And note, we will learn that if the set of partial limits is bounded, it must include the maximal and minimal partial limits that are called lim sup and lim inf. We'll talk about them later. It's like the highest partial limit and the biggest partial limit and the smaller partial limit. But because one eye or what is this rotten smiley?
No, that's how we use like smileys. We just put
With one dot?
F bracket.
no without brackets. Oh, without dots. Just brackets.
Ah, F
Because
and
there wasn't a starting bracket.
F and an ending one like
No,
this.
just a bracket.
Just the bracket is smiling.
And the more brackets there are,
But what about the eyes? It's just never heard about it.
He's blind.
Yeah, no, that's what I thought. I thought this was because of the worm, but I don't know. Okay, sorry. Fine. I feel even though this is not a theorem, I feel obligated to say, and the sequence is bounded, because otherwise it might tends to infinity and it has no partial limit. So you might think, oh, the empty set is bounded. Okay. So here the infimum of the sequence was supposed to be 0, therefore it must be a partial limit by itself. Any questions so far? And I think that is it's one of the main things, because like I said, we wish to say something smart about a sequence that does not have the limit. This is something smart. The lim is inf is the minimal partial limit, and the lim sup is the maximal partial limit. So you get kind of like a minimal limit and a maximal limit, even though you don't actually have a limit. Okay, it helps us say something smart about or interesting about sequences. And now a question: did you learn about cardinals in discrete cardinality in discrete mathematics?
By the end.
You know that the cardinality of the real numbers Aleph is strictly, just for one example, is strictly the amount of real numbers is strictly larger than the amount of natural numbers.
Yeah.
Okay, and rational numbers. Okay. Fine.
It's
We said that
and there was one that it's impossible to prove, right?
now
It's impossible to prove
No.
that there's a proof for it.
No, it's impossible to prove that there is a cardinality between the natural numbers and the real numbers. But the fact that there are more real numbers than natural numbers, that is easily proven.
yeah.
Not impossible.
By the word ordering principle. But no, yeah, we said that the amount of rational numbers is the power set of the natural numbers.
The real numbers.
The real is the power set of the natural
Yes,
numbers.
yes. That's not hard to prove. The other one is not hard to prove. It's impossible to prove. It could be that there is a cardinality between them, and it could be that there isn't one, and it won't contradict any of the axioms mathematicians use. Okay. But that's discrete mathematics. I'm not going that far. I just need for you to know that there are more reals than rational, natural. And the difference between Aleph and Aleph is why? Question: could there be a sequence whose partial limits are all of the real numbers?
Can we do the same thing we did? Actions, except
Partial limits are- Yeah, I guess
Which sequence?
I mean, the natural, can you just do the natural numbers and just like choose one index out each time? The index be the same as the number.
I didn't understand.
So you have you didn't say how many elements we need in a partial sequence for there to be a limit. So if there's a single number.
No, I did say that subsequences are always infinite.
Subsequences.
But even if you were correct, you were wrong, because that's why I asked about cardinality. A sequence is Aleph Ephes, right? The real numbers is Aleph. You can't put all of the real numbers inside a sequence. So what did you say? So it feels a bit weird because, like I just said, the cardinality of the amount of numbers within a sequence is Aleph Ephes, and I demand Aleph partial limits. But it does make sense because there are many subsequences. It's like the infinite subsets, which is a higher power than the actual. But what I like about this question, I was asked it as well as the students. By the way, I thought about sine or tangents as an answer. It probably works, but it's hard to prove. But there is a very natural and easy answer for it. Yes, take the sequence of all I just said it's natural
Subsets.
rational of all rational numbers.
Oh. I know where you're going.
Because that's it. I finished.
Yeah, no, because every fraction you can
Yeah,
represent.
yeah.
It could be-
Yeah. Because
Ah,
you can, because in every area of any real number, there are infinite rationals. It's obviously not a full accurate proof, but I think it's enough to understand why it's true. I can always find another rational later in the sequence because within this area, and then just keep getting closer and closer to any number I would like. Also, infinity and minus infinity will be partial limits of that sequence. Any questions up until now? So I have another question. Does every sequence have a monotonic subsequence?
But
Why not? I like to for you to imagine the following story. Say all of the international students are queuing up at the what do you like to get from the international school?
yeah.
You get a scholarship. Okay. So all infinite number, not all, infinite sequence of infinite number of international students are queuing up to get a scholarship from the international school. You are allowed to knock some of them out of the line, but you have to keep an infinite queue. Okay? It's on YouTube.
Oh, yeah.
Will you be able to keep only students who's queued up by height, either from the first one in the queue tallest and back, decreasing height, or increasing height? So again, the queue is given. There is an infinite queue of international students. You're allowed to take some of them out, okay? And you need to remain with a not strictly, but a decreasing queue or an increasing one.
Oh, that's
This is the very same question.
balance.
You understand what I'm saying? It's the very same question because I have some sequence of height and I want to have a subsequence which is monotonic, either increasing or decreasing.
But if you do a sequence 1, 2, 4, 8, 6 more powers of 2, that's not
That's increasing.
It's not really monotonic.
Monotonic is increasing. Yeah, of course it is. Monotonic is increasing or decreasing,
Ah.
not constant.
Oh,
It's not constant. No, monotonic. Strictly, not strictly. I should stop saying strictly. Increasing or decreasing could be constant. I don't care. Constant. You don't have to have a constant subsequence. But increasing. What do you think about that?
Increasing or decreasing?
Yes.
Yeah, there should be. Like not decreasing or not increasing. Yeah, there
Yes.
should be.
What's the proof?
We have to start taking. We have to select an n to start taking indexes from there. Either it's before that n, it's going down and then it goes up, or like in whichever
Talk to
direction.
me like I'm a compiler. Okay.
Either we have to. We know that.
We have the students. Let's talk about the students. Okay.
What did you say about the students?
The students are queued up.
Mhm.
You can choose each student in the infinite queue, whether he stays or go out of the queue.
So I mean, I can tell you in discrete math terms because I think it's easier.
Okay, well,
Because Because of color real numbers, we know that there exists a total order between the numbers.
No. You cannot reorder the cube.
No, I know, but there's an order between the real numbers. So either
The regular order.
yeah, the regular
Yes,
order.
I know. That's the height. So that's the.
Yeah,
Yeah.
so
We started with that.
yeah, we started with that. So now we
That's
know.
what discrete math does to people.
Yeah, I know.
First, there exists an order. I know it. I know.
To make a milkshake, first you create the universe.
Yes,
So
yes.
so
Take the empty set.
yeah. So we know that from each number, either it's increasing, decreasing, or staying the same. That
By the next one.
yes.
Yes.
So if we there it can be go up and down, it doesn't really matter. But we can always find points where it's lower or bigger than the next one. So we can just select if we find that the sequence is overall decreasing after an infinite period.
So assume that the first student is tall and the second one is shorter than him, and then the next one is tall and then short. Who would you take? Who do you start with first?
The shortest. I mean the middle one.
So you take the second student and then you go up or down. My point is, whatever it's not the right approach. If whatever is, if you build some subsequence, it could happen that when you continue down the way, you figure out, let's just say you started building an increasing subsequence, and then you find that everyone else is shorter than the last one you had. What will you do next? You see that's what I'm saying. You want to try?
No.
Yeah. Yeah, because that's you say we'll start with someone. If there's someone shorter, we continue, and then if we find no one shorter anymore, then we start increasing. But it could be that there are one giant and one very small person at the start, and you get stuck both on the increasing subsequence and both on the decreasing one. So it doesn't work that easily. But it is true, okay, theorem,
Oh, wait, can I try?
there exists for every sequence, there, wait for it for next time, because I won't prove it, I just want to say why is it so important? For every sequence, there exists a monotonic subsequence. And why is it so important? Conclusion, Bolzano-Weierstrass. I'm not writing it through it all, so yeah. Theorem. Every bounded sequence have a finite partial limit. Because one would ask, maybe there are no partial limits. Maybe there is no order whatsoever within the sequence. Everything just keeping jump around. So Bolzano-Weierstrass okay, and Bolzano-Weierstrass theorem says that there must be a finite partial limit, and you can understand the proof yourselves. Take a bounded sequence, it has a monotonic subsequence by this theorem, and any monotonic sequence which is bounded have a limit. Okay, so that's one of the nicest proofs for Bolzano-Weierstrass. There is another one, but that's a very nice one which I like. But it requires to prove that you can always choose a monotonic subsequence, and it's not trivial. And we'll do that and more on the next episode of Calculus 1. See you guys.
In the next episode.
In
the previous episodes.
Do you know what Stalin song is?
Silent Sword,
No, what is time sort?
Last episode.
Well,
Uh,
you can explain it pretty easy.
It's better to show it.
you have a gun.
Basically,
You're close.
Yes.
there's also Israeli sword.
I've heard of that.
Israeli sword is when you make a queue and
It's
then
unsorted, no?
you make a queue,
You
you make a queue and then you add people depending of a variable called friendships to wherever place
Oh,
the queue.
Yeah.
I
with a
thought you
friend.
make a queue and then you make it into a heap.